question. Yeah, it makes sense. I'd rather have a hard problem than open book. Yeah, exactly. Yeah, rather make the exam a little bit harder and make it open book, in my opinion, as well, than have it be easy and closed book. I want to actually test you on what you can do rather than just how much you can memorize. Okay, so yeah, last time we were discussing the relationship between entropy and the temperature, right? Um, so I think where we left off was basically we were about to start the section that Schroeder calls the macroscopic view of entropy. So let's just discuss that very quickly. Macroscop. Jesus. I cannot spell today. All right, so let us take two objects. Let's take one object to have a temperature TA with 500 Kelvin. Take another, temperature B, to have 300 Kelvin. And let's consider that over some time interval, we have some heat. We'll say it is 1500 joules, and it flows from A to B because A is hotter than B. And what we're also going to assume is that since we're going to assume that A and B are so large that adding this heat, this transfer of heat, doesn't actually change the temperatures of the two. So in that case, we can apply the formula that we had previously, which in general was just that the change in entropy is the heat over the temperature, heat added divided by the temperature. So for the case of system A, we consider that we have that this, in this situation, should be minus 1500 joules all over its temperature, which doesn't change. So it loses entropy to the tune of minus 3 joules per Kelvin. And then if we also apply that equation to system B, we should find that it gains 1500 joules of heat, but it's at a different temperature, a lower temperature, 300 Kelvin. So now its change in entropy, even though it gains the same amount of heat that system A loses, its change in entropy is plus 5 joules per Kelvin. So this one loses entropy as heat flows out. This one gains entropy as heat flows in. And the only reason that this actually happens, right, is because we're assuming that these things are so big that the temperatures are not changing appreciably. But in general, like, this is what we should always expect, is that when heat flows from one system to another, that generally the total entropy will actually increase overall, even though you're transferring the same amount of heat. Are TA and TB the... Oh, yeah. So, yeah, Deb's asking, are TA and TB the initial or final temperatures after the heat transfer? Yeah, they're both. So here we're just assuming that we've got these big old reservoirs, basically. TA is a big old reservoir of something of temperature 500 Kelvin. TB is another big reservoir of temperature 300 Kelvin. And they can exchange 1500 joules without actually changing their temperature appreciably. We'll do a lot more stuff just like this when we talk about like heat engines in chapter 4. But this is just supposed to display how you can actually gain entropy via calculations like this. So another thing we could ask is, well, what if the temperatures were the same? What if TA was at 500 Kelvin and TB was also at 500 Kelvin? How would this situation play out? Does anybody have any thoughts about that? It's really easy, but I just want you to think about this. So basically, does heat flow if there's no temperature differential? No, it doesn't flow, right? So if the only reason that heat can actually flow here is that these two are at different temperatures. So if they were at the same temperature, I mean, you could talk about like them exchanging heat, but the point is that this wouldn't happen spontaneously. And so therefore, this process would never happen. Okay, so that was just a real short calculation. Now we're going to talk about the two-state system again, and specifically how it's more interesting than some of the other systems we've talked about, like the ideal gas with respect to how it scales with temperature as a function of the energy. So paramagnetism. And just know that if you're ever looking in the literature, this is more often called the Ising model. Okay, so what is the paramagnet again? Well, oh, sorry. I'm going to have to pause for just a second. I've got a cat in my office and it's frantically trying to claw up to my door down. So give me one quick second. Sorry. Okay, hopefully that's the end of that. Okay, so the paramagnet is basically you've got some space, you've got a magnetic field going through that space. It's oriented in some direction. We'll call it like the plus z direction for now. And then you've got a bunch of dipoles that are situated in this magnetic field. Think of this magnetic field going throughout the entire space. And the dipoles, well, they can either have their spin up or they can have it down. And so they can be arranged in some number of ways, and we know how to calculate the number of ways, right? Because we know how to calculate the multiplicity for a two-state system. So generally what we do is we take the up state to have u equals minus mu b, because if you remember from like E&M, whenever whenever a dipole is aligned with the external magnetic field, that's going to be preferential, right? So it's going to be like the lower state. So we'll assign it a negative energy. And we'll assign an energy of the opposite of this to the other state. So down we'll have u equals plus mu times b, where b is just the magnetic field and mu is some conversion between magnetic field and energy, which is going to be like the Bohr magneton or something, but it's kind of irrelevant. So in general, the total energy will just be mu times b times the number of dipoles that are down minus the number that are up. And so we could rewrite this as mu b times n minus 2 n up. And we'll also define another quantity, which we will call magnetization. We'll define that as big capital M, and it's also defined via the formula mu times n up minus n down. That will be equal to minus u over b. Okay. So now let's recall that for a two-state system, we're always going to have it be the case. So I see a chat. Yeah, Safe, what's your question? Yeah, so we are adding them. So, I mean, one of them we're assigning a negative energy because it's aligned with the magnetic field, and the other one we're assigning a positive energy because it's anti-aligned. So when you add them, it's going to look like the number of them down minus the number of them up, because the number of them down contribute positive energy, and the number down contribute negative energy. Do you see? Oh, not necessarily. No. It could be positive or negative depending on the way they're actually oriented. So I mean, like the orientation I wrote right here is just something to represent what it looks like, but I mean in general, like they could be any number of directions. They don't have to perfectly balance each other. Like for example, the lowest energy state you could possibly have in this model is where n down is 0, right? And all of them are up. And so in that case, the energy is negative mu times b times n. Does that make sense? Yeah, no, they're not necessarily equal. So we're just saying that you have some number n of those guys, but they can be distributed through like n up and n down, however you please. Okay. So yeah, recall that for a two-state system, we have this multiplicity function. You would just use this on the exam. So in general, the way we're going to do it in this section is we're just going to take some numerical results for this. Because in general, for systems that are big enough, as you well know, actually calculating this in a calculator or something is just going to be insane, and doing it by hand is just going to be insane as well. So what we're going to do is we're just going to rely on some numerical results that Schroeder presents in his textbook, but you can very easily replicate this using Mathematica, Python, Root, whatever the heck you want. So if we were to calculate this across all the different possible macro states for the paramagnet, and then we were to calculate from that the entropy, and we'll divide it by the Boltzmann constant just so that we don't have to explicitly include that, right? Because S is equal to K times log of omega. So dividing by K is just ignoring that factor effectively. So just think of this as log of omega. And then we'll also plot on this axis, plot that to be U, the total energy, divided by mu times B. Again, we're just dividing by mu times B so that we can neglect the units that exist in there. So if we were to calculate this for the paramagnet that we're talking about here, what you would see is something like the following. So if we're going from minus 100 energy to plus 100 energy, for example, you would see something that goes like that. Hey, not bad. Not bad at all. Okay, so let's look at this and think about it in terms of the way that we've understood entropy and its relationship to temperature that we talked about in the previous section. So if we look at, like obviously we see that if my drawing was perfect, this point right here at the top, that would be like where entropy is maximized, right? That should be the peak, even though it looks like this is maybe a little bit taller. It's not. Something like that. So if we look at a point away from the maximum entropy, let's do that. So, and we look at the slope. So what did we say about the slope in the previous section? Does anybody remember? You might have been so busy studying for your exam that you totally just threw that out of your head. Anybody out there? So we related the slope to the temperature. Do we at least remember that? So yeah, exactly. So specifically, like in a mathematical formula, we said that 1 over the temperature is equal to, I guess I don't need this, the derivative with respect to the energy of the entropy. And so basically how you can think about this is if it's got a bigger slope on an energy versus entropy graph, as it gains energy, the entropy goes up. So it wants to accept energy. So you can think about it as being at a quote unquote lower temperature. But really all it wants to do is it wants to maximize its entropy, right? And so as it keeps on going up and up and up, its slope gets lower and lower. And so at this point right here, it really wants to, it'll gain energy very, very readily because it increases the entropy by a bunch. And remember, it wants to increase its entropy because the entropy, for the state where it's maximized, is the most probable state that's possible. So as we keep on going and going and going, eventually we come to this point, and now the slope is 0, right? Well, what does that tell us here? So if the slope is 0, so we could rewrite this as t equals the slope inverted. But if the slope is 0, 1 over 0, that's just divergent, right? That's infinity. So at this point right here, the temperature is actually technically infinite if we use this formula right here. And now we observe some even stranger behavior as we go past this point right here. So as we go past this point, we look at a point over here on this side of the graph. Now the slope is actually negative. So Now it tells us that on this side over here, t is a negative number. At this point, t is infinity. And then over on this side, t is positive number. So it's actually the case that in systems where you have a maximum and a minimum amount of energy that it can actually accommodate in a system like this, that you can realize so-called negative temperatures. But really, how you want to think about these negative temperatures is that they're actually hotter than the positive temperatures. So always think about temperature via its relationship to entropy. So over here, we only think about this as being a cold temperature because it readily accepts energy, right? Energy will preferentially flow into the system if it's in this state right here. And as it goes higher and higher and higher, now at this point, it'll give up energy to any system whatsoever, right? Because you can throw in energy, you can lose energy, and the entropy doesn't change at that point in time. But then as you move over here, as you add energy, the entropy actually decreases. So since it wants to increase its entropy, it wants to lose energy, even more so than it does when it's t equal to infinity. So that's why you should think of these negative temperatures as actually being hotter than the divergent point right here. So hopefully that explanation makes sense of why you can think about this in terms of temperature. It looks kind of wonky, but just realize that the real definition that you should always be going back to is this idea of it wants to increase its entropy, and to do that it either gives up energy or it wants to gain energy, and that's how you should think about hotter and colder. Okay. So yeah, this is an interesting thing to think about for sure. And if we were actually to plot what the temperature looks like as a function of energy, you get a graph that looks like this. So it goes, whoop, diverges off, then it comes up from minus infinity and whoop. That's like kt, u times b, that is u over n mu b. So that just nicely displays this divergent behavior right here. Don't think there was a whole lot more I wanted to ask about that. So this discussion right here was just based off of the numerical results that Schroeder presents in the textbook itself. So now what we're going to do is we're going to actually look at this from an analytic way rather than relying on numerics. We're going to see if we can. Yeah. Mm-hmm. Say that one more time. Mm-hmm. Yeah, so if you go in this direction, for sure, yeah. But it's not that it doesn't want to necessarily gain energy. In fact, it's the opposite. If you find yourself in a state over here, you can see that you want to lose energy, because what you should think about is that the system, it wants to tend toward the state of maximal entropy, right? It wants to maximize its entropy. That's the second law of thermodynamics. That's what we're basing this entire idea off of. So basically all we're saying is that if you're over on this side, if you've added so much energy that you're now on this side of the entropy versus energy graph, now you can think of this state right here as being effectively hotter than all of the states over here, because it'll readily give up its energy in order to move back over here to the maximum state of entropy. Does that make sense? I wouldn't. No, definitely not. So it'll just go straight up and it'll level out right there. Yeah. I mean, yeah, well, I mean, there might be some kind of oscillatory behavior, but I guess we're not necessarily talking about like the actual the way this system would like behave dynamically in real time. We're just talking about like if it's in this state, it wants to gain energy. We're just talking about its relationship to temperature right now. I do think, yeah, there would be some kind of oscillatory behavior, but generally you'll have some kind of damping as well. And so it'll tend to the state right here. But yeah. Mm-hmm. No, and that's actually a good question that I definitely should have said. So this point over here, so the most negative point, right? This point right here corresponds to what exactly? Well, if we go back, we see that we're assigning a negative energy to the up states and a positive energy to the down states. So if the energy is as negative as possible, then this should just be the state where all the dipoles are aligned with the magnetic field, right? On board with that so far, at least? So then this state over here, the far right end, the most positive point, that would be where all the dipoles are completely anti-aligned with the magnetic field. And it makes sense that the entropy here is 0 and the entropy here is 0. And do we know why? Why does that make sense? That the entropy should be 0 for the state where they're all up or the state where they're all down? Can anybody answer that? Yeah, I mean, it is, but so think of entropy in terms of microstates. So how many microstates correspond to the state where they're all up? And how many microstates correspond to the state where they're all down? There's just one. Yeah, exactly, Deb. So there's only one state that you can have where all of the dipoles are anti-aligned, and there's only one state you can have where they're all aligned, right? So it makes sense that the entropy is 0 at these points right here. Likewise, it then makes sense that this maximum entropy right here, this corresponds to the point where all of the dipoles are randomly aligned, or like 50% are up, 50% are down. Just because there are more ways to make that exact state, because all of the dipoles look the same and are identical. Does that answer your question at all, Jerry? What do you mean? So this graph right here is for the whole system. It's the system as a whole. Well, we're not talking about like a, yeah, no, that's right. Yeah, so if it's at its equilibrium point, then yeah, they're just randomly distributed. They're half of them are up, half of them are down. If it's come to an equilibrium point, yeah, then it's sitting right here, and half are up, half are down. Is that what you're asking? You're asking about like what each of the dipoles look like at this point? Okay, yeah, that's what would happen right there. Okay. All right, so go to the next page, buddy. What happened? All right. Okay, so that was just a discussion of the numerical results that were presented in the book. Now we're going to go through the analytic discussion. I had just written this. I don't know where the page went. So I had just written this multiplicity function. Let's hope it doesn't disappear again. Okay. So let's assume that in this paramagnet, the number of dipoles for the up dipoles and the down dipoles are both, they're separately very, very large numbers. So let's consider log of omega. That'll just be ln of n factorial minus ln of n up factorial minus ln of n down factorial. And so we can rewrite this one right here, the n down, just because it's constrained to be equal to n minus n up, because the number of oscillators are constrained here. We're not taking them in or putting them out in any way, shape, or form. Okay, so we can approximate this as we always do, just using good old Stirling. And at this point, you do a little canceling. So you've got this term exactly balances this term and this term. So they all go sayonara. Okay, so we've got log of omega. What we want to do is we want to find an expression for the temperature. So let's recall again how we relate the temperature to the entropy. So we said that 1 over temperature is just the slope of del S del U. And this is with N and the total energy held constant. In this case, we'll say B, the magnetic field, is held constant because that's the thing that's determining the energy. Okay, so if we expand this out, S is a function of N up, so we can rewrite this derivative as derivative of N up with respect to U times the derivative of S, the entropy, with respect to N up. So these two things are equivalent. And then we can take the derivative of this expression right here with a k out in front of it. Oh, actually, I think we leave that off. Yeah. And we should get 1 over 2 mu b. Oh, wait. Yeah, sorry. Del S, del n. Okay, so from that step to that step, I just took the derivative of n up with respect to u. And then there's a number of more steps in here, not a whole lot. But you should get that 1 over the temperature is 2 times mu times b log of n minus u, the total energy, divided by mu times b, over n plus total energy over mu b. Okay, so at this point, you just want to solve for u in terms of the temperature. So you could either do it by hand, or you could just pop it in Mathematica, tell it to solve, do the work for you. You've got your own assistant. So if we do that, we have that u is just going to be mu times b times n times the quantity, 1 minus e to the 2 mu b, all over k times t, all over 1 plus e to the mu b, all over k times t. Now at this point, does anybody have any thoughts about what this expression looks like? Is anybody familiar with stuff that looks like this? How many people are familiar with like the exponential? Yeah, Hanch. I like the extra C on that. I assume like people for the most part are familiar with like the exponential representation of the trig functions. Just of like representing cosine and sine in terms of e to the I x plus or minus e to the minus ix over 2 or 2i. I wrote up a little thing in a Mathematica file to just show people that this is definitely the case if you haven't seen it before, or if you're not so familiar. So give me a second. So if you're ever in doubt about stuff like this, you can just hop on Mathematica. So it's true that if you look at the trigonometric function sine, and you take its Taylor series expansion, that you can line up that Taylor series expansion term for term for term, on and on for infinity, to the trigonometric expansion of e to the ix minus e to the minus ix over 2I. So I'm just displaying that right here. So you see that this is this is this, that is that, and on and on and on. So sine x is equal to this right here. You can do the same thing for the hyperbolic sine and the hyperbolic cosine. And that just ends up being exactly what we're going to show right here. So this right here can end up being rewritten in terms of the hyperbolic tangent. And the hyperbolic trig functions are just trigonometric functions for hyperbolas rather than the usual trig functions that you use to for circles. So they just project onto the x or the y-axis for a hyperbola. So yeah, let me just say real quick, the way that you'd arrive at this is just by saying that sine h of x, or sinh, I don't know why people say sinh, there's no C in here, but that's what every single person in the world I've ever met says. So that's sine hyperbolic. This is the hyperbolic cosine, or cosh. And of course, just the hyperbolic tangent is just equal to sine h of x all over cosh of x. And you can show that taking these two expressions, putting them in there, you can get them into a form that just looks like this right here. So that's that. So now let's recall the magnetization. Magnetization was defined as minus u over b, the magnetic field. So now, since we have u as a function of t, we just wrote it previously. It's right there. This is u as a function of t. Then we have that the magnetization, which is generally a quantity that you can measure, looks like this. And if we were to plot this, oh, no. Now I'll just write of x because it doesn't really matter that much. The general feature is that, whoop, like that. So when t is small and positive, m is maxed. So when t is small in here, this argument right here gets really, really big and positive since t is small and positive. So you're over here on this end. And the magnetization is at a maximum. So we'll keep on going. So when t goes to infinity, you see now that this becomes 0. So the magnetization goes to 0. And then just the mirror happens for when you go to negative temperatures. So this should make sense to you because basically the magnetization is just a measurement of the alignment of the dipoles with the magnetic field. And so as the temperature gets really, really big, these dipoles want to just flip around randomly because they've got so much energy. They're just knocking into each other, jostling all over. So they're not going to be very easy to align into just one direction or the other. So that's why the magnetization goes to 0. And then as you look at very, very small positive temperatures, you get it way out here because obviously like you cool them down, but it's still technically a positive temperature, but you've cooled them so that now they're a lot more able to be aligned to the magnetic field. And then the opposite is just that you heat them up a ton, make them into a negative temperature, and again, they're going to do the same kind of feature. So this is an interesting system, which you'll definitely treat in the future if you ever go to grad school or study physics at any more detail. Question? Yeah, Jacob. Mm-hmm. So you're questioning the, oh, I'm hearing a bunch of echo. So you're questioning the relationship between temperature and entropy? Is that? Let's go back here. I think I see what you're saying. It does. And so, yeah, I mean, the reason you can relate it to temperature in this way is just that like the real like core, like the foundational truth that we're working with here is that you always have where is it? This relationship holds between these two quantities that we call entropy and temperature with respect to energy as well. So like this is our core belief basically. And so we're just saying that we have a system, we'll call it the Ising model, paramagnet, whatever. We can write down its energy in some way. And then we can calculate how that energy changes with respect to the temperature. So I mean, we're really just we're just equating the two because this system does have energy, so therefore it does have a notion of temperature. I don't know if that really helps at all. No, it's not obnoxious at all. I mean, I get it. Nothing. And you can do that. Yeah. Yes. Yeah, yeah, yeah. Yeah, I mean, so thermodynamic quantities, they don't just apply to like your typical ideas of what energy, temperature, and all that are. I mean, we've already seen like our notion of temperature kind of break down, right? Like intuitively, you would think that negative temperatures are going to be way, way, way colder or something like that. But I mean, don't follow your intuition too hard here because it's not gonna lead you in the right direction. Follow the math. Is really all I'm gonna say. Yeah, but I mean, yeah, there's a whole field of physics that deals with what's called black hole thermodynamics, because it turns out that the quantities that a black hole has, like its conserved quantities, they actually obey a kind of thermodynamic relation as well. So you can talk about like a black hole temperature and all kinds of stuff like that, which I'm sure you guys have heard before. There's also like this big debate about like the black hole information paradox, right? And that deals with entropy and notions of temperature and all of that. So yeah, I mean this stuff doesn't just apply to your typical ideas of temperature and entropy and whatnot. Where were we? Well, I guess we're technically done. I've got about like 8 more pages of notes that I want to cover. So maybe I will just record this like later tonight or something, or we can even go through it maybe next week because chapter 4, at least from what I've written so far, is going to be fairly short compared to what we've talked about for the other chapters. So maybe I'll just hold off and we can talk about chapter 3 and then chapter 4 all next week. Um, and leave this for now so you guys can have a bit of a break over the weekend. Are there any other questions about anything? Hopefully this is making some sense. All right, well, if there aren't any questions, I'll let you go. I'll have office hours right now. If you want to ask questions about exam problems or anything, feel free to show up. But yeah, we'll talk more about Chapter 3 next week. I'll grade your exams, and then we'll also do Chapter 4. So hope you all have a good weekend, get some rest, and get ready for another week of Thermo. Okay, thanks.